and welcome to my presentation on the CIRCE mission, a joint UK-US space mission scheduled to launch in 2021. My name is Alex Ekathangelou, a space scientist at DSTL and technical support for one of the UK payloads, TopCat. I've had the fantastic opportunity as a recent graduate to be involved with the UK side of this project from the start, and today I will give you an overview of the CIRCE space mission and the scientific benefits we hope that it will provide to both the UK and the US. CIRCE is a collaborative space mission between DSTL in the UK and NRL in the US, developing the small satellite ionospheric physics capabilities of both nations. We have built upon the strong relationship of joint research and collaboration to address new emerging priorities for both nations, such as our understanding of space weather and small satellite capabilities. Key areas of interest that CIRCE will address include our understanding of space weather, our space situational awareness capabilities, and development of options for affordable space missions. The CIRCE mission will investigate the ionosphere, an ionized region of the upper atmosphere that is formed due to solar radiation ionizing neutral particles in the atmosphere. This charged plasma interacts with the electric and magnetic fields in the near-Earth environment, and despite being far less dense than the rest of the neutral atmosphere, it significantly affects the structure of the upper atmosphere as a whole. The free charged particles in the ionosphere have an effect on radio waves, transmitting, refracting, and even reflecting them, depending on the density of the plasma that it passes through. While overall the climatography of this region is fairly well understood, the ionosphere exhibits a remarkable short-time variability in response to space weather events, such as solar flares, coronal mass ejections, as well as dynamics driven by the lower atmosphere such as waves, tides, and circulation. The resulting disturbances and structures in this charged region can dramatically affect how radio waves propagate through it, sometimes even completely disrupting them. These effects can significantly interfere with technologies such as communication links, geolocation systems, and radar, which rely on the propagation of radio waves. It is therefore vital that we develop an understanding of these dynamics in order to be able to determine the origins of disturbances to systems, discriminate between environmentally driven effects and technical malfunctions, and overall enable better space situational awareness. Additionally, understanding the charge structures that form in this region allows engineers to better protect equipment and personnel from the effects of space weather and provide a more resilient space capability. The objective of the CIRCE mission, therefore, is to accurately characterize this dynamic ionosphere. CIRCE will be launched in 2021, supported by the US Department of Defense Space Test Program, into a circular inclined 500-kilometer orbit. The mission will exploit multiple sensor measurements across a constellation of 2 satellites to characterize the short timescale dynamics in the ionosphere. The 2 satellite buses, provided by Blue Canyon Technologies, will fly in a lead-follow configuration, maintaining a separation of between 250 and 500 kilometers using differential drag. This separation will allow the 2 spacecraft to both observe the same region with a short time delay in between, allowing short timescale dynamics to be observed. Each spacecraft will carry an identical complement of 5 scientific payloads, contributed from industrial and academic partners across the 2 nations. DSTL in the UK is providing CIRCE with the In-Situ and Remote Ionospheric Sensing, or IRIS, suite. The IRIS suite showcases the capabilities of UK academia, comprising 3 highly capable scientific payloads provided by British academic partners in a compact 2U volume. The IRIS suite will provide in-situ ionospheric particle and radiation measurements, coupled with the remote sensing of GPS signals to derive the electron density of the ionosphere. DSTL is providing 2 IRIS suites to the CIRCE mission, with one installed on the front 2U of the lead spacecraft and the other in the rear 2U of the trailing spacecraft. The time delay between the 2 spacecraft passing through the same region of the upper atmosphere will allow IRIS to observe environmental changes over short timescales. The datasets derived from the IRIS payloads are anticipated to improve our understanding of the variability of properties such as atmospheric drag and the chemistry of the thermosphere, and to measure the impact of space weather and other effects on the upper atmosphere. Future space missions will benefit from the IRIS datasets, which will highlight regions of higher radiation in Earth orbit, helping to shape orbit designs and inform radiation shielding requirements. Additionally, IRIS will validate the Midas tomography algorithm for characterizing the topside ionosphere using differential phase to infer total electron content. In addition to providing substantial scientific interest alone, the sensors comprising the IRIS suite will enrich the scientific output of the US tri-tip payloads, providing contextual environmental data alongside the UV photometry measurements of electron density. Developed by University College London's Mullard Space Science Laboratory, the Ion and Neutral Mass Spectrometer, or INMS, is a highly compact 1U electrostatic particle analyzer. INMS is capable of measuring a range of ionized and neutral particles in the environments that the spacecraft passes through. INMS has proven flight heritage, having successfully flown on Cubesat in 2014 and the QB50 missions in 2017. INMS can operate in two modes. In neutral detection mode, the ion filter rejects incoming ions and the ionizer charges any remaining neutral particles, allowing them to be detected and measured in the analyzer. In ion detection mode, the ion filter and ionizer are disabled, allowing incoming charged particles to be measured whilst neutral particles pass through a gap in the analyzer undetected. INMS will alternate between these two modes. The INMS sensor on the lead CIRCE spacecraft will permanently face the RAM direction to collect incoming atmospheric particles, while the trailing spacecraft will periodically rotate, allowing INMS to operate in the RAM direction of the day side of the orbit, whilst the US tri-tip payloads operate during the night time of the orbit. From the University of Bath in the UK, the TopCat-2 payload is a triple-frequency GPS receiver. As I previously mentioned, the variable density of the ionosphere can interfere with the propagation of radio signals passing through it. TopCat-2 is designed to measure the differential phase of received GPS signals, from which the total electron content of the medium can be derived. This electron content measurement allows for four-dimensional mapping of the electron density of the ionosphere. The payload itself consists of a GPS receiver, payload controller board, and triple-frequency antenna. TopCat has previous flight heritage. TopCat-1 was a PhD project demonstrating the use of commercial off-the-shelf, or COTS, hardware for use in a scientific upper atmosphere payload. It was flown on the UCube mission in 2014, and our TopCat-2 payload is an updated model based on this design. TopCat-2 features a new GPS receiver and an upgrade from dual to triple frequency capabilities. Total electron content tomography is a well-established method of imaging the ionosphere, first demonstrated with LEO satellites on the US Navy Ionosphere Monitoring System and the Russian Cicada satellites. Radmon 3, provided by Sorry Satellite Technology Limited, is the latest in a series of mature radiation monitoring payloads. Radmon is a real-time, low-swap instrument which provides data on the radiation experienced by the IRIS payload. The payload utilizes three RadFET solid-state dosimeters to measure the total ionizing radiation dose experienced by CIRCE in different locations around IRIS. An ultraviolet photodiode is used to monitor dose rate, while a large area PIN diode detector measures proton and heavy ion fluxes. To date, 6 spacecraft have flown with SSTL-developed radiation monitors in a wide range of orbital regimes. These demonstrate the veritable spaceflight heritage for this technology and have provided a near-continuous dataset of geomagnetic radiation environment readings since 1992. With 2 identical Radmon payloads in the same orbit, datasets from both CIRCE spacecraft can be used to cross-calibrate the sensors, as well as providing a comparison for identifying system upsets and anomalies. Datasets from Radmon are anticipated to benefit the development of orbital radiation models and demonstrate the increase in particle flux and radiation in the region following space weather events. The 3 payloads that comprise the IRIS suite are compact enough to fit into a 2U volume, which, as shown here, makes up a self-contained sensor suite that is installed onto the rest of the CIRCE bus. The F region of the ionosphere, occupying altitudes from about 150 to 500 kilometers, emits several discrete wavelengths of far ultraviolet light. These emissions are known as night glow and are often used to observe and characterize the ionosphere. Observing these emissions from space is ideal, as the lower atmosphere completely absorbs these wavelengths, preventing any background light from the surface from interfering with observations. First developed by the US Naval Research Lab for the COSMIC mission, the Tiny Ionospheric Photometer, or TIP, is a highly compact remote sensing instrument designed to observe this night glow and thus measure the density and physical structures of the ionosphere. The tri-tip payload contains 3 of these sensors, hence tri-tip. NRL are providing 4 of these tri-tip instruments, which each fit into a 1U Cubesat volume. 2 sensors will be installed on each of the CIRCE spacecraft, providing 4 unique lines of sight down onto the same region of the ionosphere below. The in-track separation of the two spacecraft is designed to optimize this viewing geometry, allowing for multi-point sampling of the ionosphere. These observations will take place on the night side of the orbit when the night glow is most visible. In the daytime, the trailing satellite will flip 180 degrees, allowing the INMS payload on the IRIS suite to align with the RAM direction instead and collect data. Understanding the dynamics of the ionosphere is vital to the operation of various ground-based technologies and spacefaring interests. The CIRCE mission will provide insights into the dynamics of this region of our atmosphere and highlights the considerable scientific capabilities that can be achieved by small Cubesat missions. The delivery of the IRIS payload in just 1 year demonstrates the agility of the UK space industry and showcases the capability of UK academia to enable high-impact space science. Thank you very much for listening to my presentation of the CIRCE mission. Many thanks to the SmallSat conference organisers for making all of this such a virtual success.